In 2024, Indonesia recorded over 210,000 dengue cases and more than 1,200 deaths. In Yogyakarta alone, 4,027 cases were reported, with Sleman and Gunung Kidul among the hardest hit regions.
But behind these numbers are the real stories.
We met Mr. Edi Prastowo, a father from Sleman, who shared how both he and his child suffered from dengue. He described the pain, the delays in treatment due to BPJS referral systems, and the tragic loss of neighbors, including a 4th grade student.
Vaccines such as dengue vaccine and dengue are introduced, but the access remains limited.
Dengue, for example, can cost up to 745,000 rupiah per dose, making it unaffordable for many families.
The price barrier in Indonesia depends on imported pharmaceutical raw materials highlighted the urgent needs, locally produced and affordable vaccine components.
Molecular farming offers a promising solution. By using plants to produce recombinant proteins, this approach can reduce production costs and simplify infrastructure, making vaccines more accessible to low and middle-income populations.
Inspired by this potential, we explore which plant in Indonesia could serve as viable plant molecular farming platforms.
Our goal was to find a system that was not only scientifically feasible, but also socially and agriculturally relevant. Our choice fell on Nicotiana tabacum, a plant with proven protein expression capabilities and deep cultural roots in Indonesia. In a region like Jember and Temanggung, tobacco has been cultivated for generations, forming the backbone of local economies and traditions. At the same time, tobacco carries a negative stigma due to its association with smoking-related health risk.
Through this project, we want to show that tobacco, when we repurpose for biomanufacturing, can offer positive impact too.
We set out to transform this legacy crop into a scalable biopharmaceutical protein production chassis, combining molecular farming with existing infrastructure and community expertise to support public health and reshape tobacco's role in Indonesia's future.
We set out to engineer Salty, a salt-inducible TYDV-based expression system for recombinant protein production in Nicotiana tabacum.
The project focuses on producing the enveloped domain 3 or ED3 of DNV2, a promising subunit vaccine candidate against dengue fever. To support promoter engineering, we built NiSPOT, Nicotiana Stress Region Predictor and Observation Tool. In parallel, we developed a protein mutagenesis pipeline to optimize ED3 vaccine candidates using consensus scoring across multiple protein language models.
Together, these tools enabled a streamlined workflow that integrates dry lab prediction with wet lab validation.
This integration accelerates design iteration, reduces experimental uncertainty, and improves resource efficiency.
Salty bridges molecular farming innovation and social relevance, grounded in Indonesia's unique agricultural potential.
To ensure that Salty was not only scientifically sound but also socially and culturally relevant, we began with a series of human practices. Our work has been guided by a simple yet profound golden circle, always asking why we do this, how we can do it responsibly, and what actions we must take. This circle became our compass, ensuring that we seek perspectives from all sides before moving forward. We visited Temanggung and Jember, two regions rooted in tobacco cultivation, where we engaged directly with farmers and community members. In Temanggung, we learned how tobacco is viewed as a legacy crop passed down through generation and tied to local identity. In Jember, we explored the Tobacco Museum to understand the historical and industrial role of Nicotiana tabacum in shaping regional pride and livelihoods. To complement our cultural grounding, we also consulted experts across multiple domains. Clinical and epidemiological advisors guided us on dengue vaccine priorities, while plant biomanufacturing experts helped shape our chassis selection and workflows. We also received input from advisors in bioinformatics and system biology. This insight strengthened Salty's technical robustness and ensured our design stayed aligned with Indonesia's real needs.
We developed an integrated plant-based expression system combining TYDV, tobacco yellow dwarf virus replicant technology, a salt-inducible promoter, NiSPOT for promoter refinement, and a Consensus Mutagenesis Pipeline for protein design.
Existing expression systems, such as constitutive promoters and ethanol-inducible switches, often suffer from low yield, proteinability, or growth inhibition. TYDV addresses yield problem by amplifying the gene of interest up to 120-fold compared to 35s in plant, making it ideal for vaccine production.
However, its common ethanol-based switch is constitutively expressed and can stunt plant growth. We replaced it with a salt-inducible promoter from date palm.
This promoter responds to inertial stress and is safer, cheaper, and easier to apply, especially in hydroponic setups, and it's ideal for controlled growth and inducible expression.
To overcome the challenge of long, poorly annotated tobacco promoters, we built NiSPOT, a Python-based classifier that identifies stress-responsive and non-stress regions using fine-tuned genomic language models.
NiSPOT identifies stress-responsive and non-stress regions, guiding promoter trimming and also construct design. And it reduces assembly errors and improves stability. For protein engineering, our Consensus Mutagenesis Pipeline integrates multiple language models and gradient-based tools to rank mutation candidates. This approach provides robust and reliable predictions, accelerates design workflows, and enables deeper explorations of protein fitness landscape.
We engineer Salty through 3.5 TPDL cycles, each targeting a distinct technical challenge.
The first two cycles focused on building NiSPOT, a promoter classification tool for Nicotiana tabacum. The third cycles developed a protein mutagenesis pipeline to optimize ED3. And the final half cycle focused on chassis preparations and construct deployment.
In cycle 1, we evaluated two pre-trained DNA language models for classifying stress-responsive promoter sequences in Nicotiana tabacum, while also initiating domain-specific pre-training for DNA PERT2 using TN90 and NITAP 4.5 genomes.
Our goal was to build labeled datasets via motif-based annotation with VIMO, fine-tuned models on sequences labeled as stress-responsive or non-stress, and assess performance across imbalanced and balanced datasets. The results revealed that the model trained on the imbalanced dataset predicted all sequences as non-stress, giving a false sense of accuracy while failing to learn meaningful patterns. With the balanced dataset, accuracy dropped to 54%, roughly the same as random guessing. This suggests the sequences were still too similar for the model to learn effectively.
Although the enabled Nicotiana pre-training was initiated, it remained unevaluated. And then we learned that our labeling and dataset correction require major refinement to support meaningful learning. To improve model generalization and reduce redundancy, we applied a CD-HIT-EST with an 80% similarity threshold and built NiSPOT, a Python CAI tool for promoter stress classification using fine-tuned language transformer models.
Inspired by literature on protein sequence classifications, we removed over 30% similar sequences to prevent overfitting. Simultaneously, we prioritized practical and reproducible software development by implementing CLI tools. The enabled Nicotiana achieved 75% accuracy, outperforming other models, the 2 and Mistral.
NiSPOT successfully executed both region-level and promoter-level classification on sample DNA sequences. Cycle 3 focused on protein mutagenesis to optimize ED3 protein sequences for vaccine engineering.
It begins with mutation exploration. We use ESM2, masked language models, and ESM-Santo that identify and screen potential mutation sites. Mutagenesis generation follows, leveraging EvoProtGrad and EvolvePro to propose single mutation candidates based on optimization algorithms. High-confidence mutations were virtually validated using delta-delta-G and structurally predicted by AlphaFold. These findings revealed the stabilization hotspot for protein core integrity and stability hotspot as a promising targets for vaccine design and recombinant protein optimization. To produce recombinant ED3 in Nicotiana tabacum, we begin with CMV35's promoter constructs. We redesigned the chassis with tobacco yellow dwarf virus or TYDV replication system to enhance protein yield, and salt-inducible promoter from date palm to regulate the final construct that includes TYDV components, RAP-RAP-A, clear, sear, and synthetic intron. The binary vector was amplified and assembled with synthetic gene insert, including promoters, TYDV, and the gene of interest using golden gate cloning. Plasmid were transformed into E. coli, DH5-alpha, and Agrobacterium tumefaciens for delivery. Plasmid yields enhanced using terrific growth. Protein expression and detection are planned via agroinfiltration and salt shock, followed by histag purification or EGFP fluorescence analysis. Tobacco varieties Kumloko and Besuki were successfully grown in hydroponic system.
Here is what we found from our experiments.
Promoter sequences were validated and used to train DNA-bred Nicotiana, which reached 75% accuracy. NiSPOT reliably performed both region and promoter level stress classification. The integrated pipeline identified stability hotspot S1 and Q49 and destabilizing residues M4 and W93. These insights provide actionable strategies for vaccine optimization. Nicotiana tabacum grows to full biomass in 2 until 3 months and performs best under hydroponic conditions. Besuki and Kumloko varieties showed larger leaf areas and more precise salt delivery. The salty system was successfully cloned and assembled. PCR verification and vector amplification and also plasmid mini-prep were optimized. Agrobacterium transformation succeeded, though protein expression and inducibility verification are ongoing.
These findings bring us one step closer to building Indonesia's molecular farming future.
Through SALTI, we learned that plant molecular farming remains underdeveloped in Indonesia. Public familiarity with the technology is still very limited. Many urban students had never heard of it, and in rural areas, basic literacy challenges made science communication even more complex. One woman in Gunung Kidul asked, "If the vaccine comes from tobacco, do we boil or chew the leaves?" That moment reminded us that innovation must be accessible, culturally grounded, and inclusive. To address this, we designed a dual strategy: technical readiness and social accessibility.
For sustainability, we discussed with several stakeholders such as Bio-Pharma, Bio-Pharma, BPOM, BPJPH, KKHPRK to align SALTI with Indonesia good manufacturing practice, halal mechanism, and biosafety standard.
For public trust, we worked with psychologists and science communicators to create inclusive outreach tools, a colorblind-friendly storybook, The Adventure of Bacterioman, a synthetic biology card game, Quartet Genetic, translated thingy posters, radio broadcast for rural and visually impaired audiences, and community events tailored to local calendars and customs. SALTI is more than a vaccine design. It's a step toward making science in Indonesia accessible, trusted, and useful for everyone. But none of this would have been possible without the people who supported us. We are deeply thankful to our advisor and supervisor who guided us through every challenge. We also thank our sponsors and partners for giving us support to make it real. From fixing PCR problems to improving plant growth, every step was built on collaborations. This project reminded us that pushing for innovation also means paying close attention to the realities around it. In Indonesia, synthetic biology and plant molecular farming is still emerging. Regulations are not yet fully in place, industry infrastructure is limited, and public familiarity remains low. This experience highlighted the importance of making innovation inclusive and grounded in local contexts. To do that, collaboration across disciplines is essential. Scientists, communicators, educators, and policymakers all play a role in bridging gaps in understanding and access. Even though the ecosystem is still growing, we hope Salty can spark something meaningful, a starting point for science that is rooted in local realities, inclusive, and open to new possibilities. Molecular farming may be a novel approach in Indonesia, but with thoughtful collaboration and community-centered communication, we believe it can evolve into something impactful and worth exploring.